This is a presentation regarding performance measures. So we're going to talk about the accuracy, weight cost sensitive accuracy lift. Most of the time you heard about the precision recall, which is tightly related to the F measure. We'll talk a little bit about break-even point. And sometimes, maybe most of the time, you heard about the people talking about receiving operative curve, which is ROC, or area under the receiving operative curve. So it's IU ROC. The first two letters stands for the area under and then ROC. So we'll talk about this. So those are very oftenly observed in the machine learning, especially those days, more and more discussion and usability in terms of the discrete regression and classification. So you end up actually trying to predict, ranges where the parameters may end up, right? So therefore, you do less continuous regression, but you do more on the discrete regression and classification. And the project I'm going to talk on the CFI protein, we also will convert data into the bin, so you will see why we're doing the binning, normalization, etc. So okay, let's start with the metrics. So first of all, obviously, let's call about the precision recall is one of the popular metrics or parameters people use to assess the quality of their model and compare between different algorithms. So precision, it could be defined as how many of the return documents are correct, and a precision threshold. So you basically can identify those parameters, and I'll give you a little bit more concrete definition in terms of the false positive, false negative once we look at the confusion matrix. Also, you can define the recall, and then you can define other metrics, which will be a combination of the precision recall, which is related to F measure norm. So let's have a look at the matrix. Confusion matrix is something you can get in the following format. So usually you have an X is a predicted label and the Y is a true label. So you basically are trying to classify the patient, or you bin the data, and then each bin is basically your cohort, and you're trying to see where the sample will end up in that bin, which corresponds to the certain range. But the bottom line that you're going to get matrix either 2 by 2 if you have only two classes, two cohort, or two bins, or you could get 3 by 3, you could get 5 by 5, depending on the number of categorical label you have in your data. So in the next question, of course, you want to some sort of characterize that matrix and then come up with some characteristics which will tell you is your model working correctly, you're getting reasonable answers, etc. I think intuitively it's all clear. It should be clear. So if you have only dark blue, especially if you look at the right bottom corner, so you will see that this is dark blue and then light blue. So obviously if you all do that elements on the diagonal, so it means that you have a spot on match. So whatever was predicted, it does correspond to the true label. So in all the patients, all the samples in your database end up in the right bin, right cohort, or right class. However, obviously life is not perfect, and sometimes you would get, actually very often you would get off diagonal blocks, and those are off diagonal blocks definitely will define the quality of your machine learning algorithm. So closer there to 0 is better your model. Intuitively is also clear. But let's define some of the characteristics which basically can be used. So accuracy can be defined if you are looking at the 2 by 2 matrix, which was present on the previous slide. You can obviously define the ratio between true positive plus true negative divided by the total population. So this is characteristics which will definitely help you to identify and compare one confusion matrix versus another confusion matrix. Let's imagine you generated two confusion matrices coming from two different models. Then you can compute the accuracy and compare them to each other. So obviously accuracy is a ratio of correctly predicted observation to the total observation. So, and that's probably kind of intuitively is also clear, right? So, so again, let's just make sure that we understand what is a true positive. So it's the number of correct predictions that accuracy is in positive, and the true negative, the number of correct predictions that accuracy is in negative. I think we are also all very familiar, and we are using that very often in a lot of science, life science projects and problems. So precision, on another hand, is defined as a true positive divided by the sum of true positive plus false positive. So again, this is a definition, and then we can use precision recall to come up some sort of harmonic average of those two quantities, and then we can derive FOM1 score. So most of the time when you're using the machine learning, so you don't need to implement those expressions. Actually, there are already libraries which you just can call, and then for the given confusion matrix, they can give it to your output, and you would know those characteristics for the given confusion matrix. So you also can have a look at the threshold. The threshold would, depending, how do you do the classification. So by the threshold, you can always adjust the confusion matrix, and obviously it will affect your accuracy and precision recall. So therefore, we need to bear in mind that those are parameters really adjustable depending how you do build your prediction versus true labeling. What is your algorithm? What is your strategy? So if you look at the curve, which is basically show your threshold versus the accuracy, you can construct the curve. That's not receiving operating curve yet, so we'll come to that point. But it's still a very important curve in terms of getting the idea for you to see how would be the accuracy performed depending on your threshold, right? And again, this threshold maybe not necessarily at the point of actually deciding to which class it can be. It could be the threshold you use, let's say, filtering the data or smoothing the data. That's one of the parameters, and it may propagate towards the final stage, and then you can compute the accuracy. So, and then by analyzing that curve, you'll see what would be the optimal threshold in your data preparation step, which results in much better accuracy later on. Or you can, better answer would be not just to provide one accuracy point and one threshold, but would just give it a median value and then the confidence interval, both on the accuracy and on the threshold level. So, okay, again, what are the problems with the accuracy? So it assumes the equal cost for both kinds of error. So cost of class B versus class C. I mean, we are talking about the obviously off-diagonal term of the confusion matrix. So if you say 99% accuracy is good, it can be excellent, it can be good, it can be quite actually diverse answer. It's not really representative sometimes, so they have to be very careful. Maybe better to look at the two parameters, which is independent in that case, and which covers, effectively how good is your top diagonal block and the bottom diagonal block. So there are other characteristics, let's say sensitivity and specificity, which is also used sometimes in the analysis, and we can talk about them later on during the case study. And again, I just show you a couple of examples here to demonstrate that what could be the potential interpretation and percentage reduction in error, what kind of it could mean. So in our characteristic is the lift function. It's not that so commonly used. It's just for, maybe it's used in the marketing and in some other financial situations. I haven't seen that too many often in a biological application, because most of the time sensitivity, specificity, recall, and F1 measure, those are parameters which is heavily applied. But let's just mention to you in case somewhere that pops up, you will be able to recognize it. So, and of course, you can build the distribution curve, right, of how much better than random guessing you can get versus a fraction of data predicted true, and then you can identify some sort of an optimal point, based on this curve, and make some other additional analysis. So we're not going to do it during our study, but we'll look at the sensitivity specificity in the case we're going to look at later on. What else is important to look at the precision recall? That those are two characteristics that obviously define very differently, and then looking at two of them, it's given much better representation where you are for the different thresholds, some of the parameters. So you can actually construct that curve And then you can look at the optimal point, and then you can see where you have a worse performance versus better performance, and then where's the break-even point. So, and that allows you to identify some sort of every necessary threshold for some of this stuff, and then use that threshold later on for the further analysis and further predictions. So what is the receiving operation curve? So that's one of the concepts, you know, where you plug in the rate of the true positive versus the rate of the false negative. Those are type of data you can displace, and then you can estimate. Obviously, the rate will depend on the threshold, and the threshold is something which is a part of your model. So you basically perturbate the threshold and you obtain the different realization, different results. For example, threshold could be just how much, what is the percentage you need to use for your training data set out of your entire data. That's one of the parameters you can vary. And then for each of the percentage of the amount of the data used in your training data set, you compute those characteristics, and then you put the point, and then you draw the curve which connect those points, and that will be your receiving operating curve. So let's have a look at the some of the examples. So obviously, it's a plot which shows like true positive rate versus false positive rate. Obviously, it can be expressed in terms of the sensitivity versus specificity, and then in terms of the probability. So here, for example, you see that the sensitivity is actually is the same as a recall, and you know, across the different applications, sometimes you can see recall and sensitivity. It's the same formula, but depending on the application, depends on the community. Sometimes people use sensitivity and sometimes they use recall as a definition. It's also related to leaf numerator, but it's less common in the literature, so you won't be able to see it that often. And then, of course, the specificity can be expressed via sensitivity, and you know, you can derive, you know, the formula which will show you how good your bottom, so in a confusion matrix, how good is you approximating your bottom diagonal block and how many elements you have off diagonal. So if I vary that threshold, let's say my threshold is percentage I use in my training data set, so I could let's say start doing, you know, 60% I'm using for the training data set, and then 40 for the test data set, and then I computed the true positive rate and the false positive rate on the test data set. So obviously, and if let's say I do it for 61% for the training, for 62, and so on until let's say 95%, I'll get a lot of points, which will obviously lead to different true positive rate and the false positive rate. And I actually can draw the line, which, you know, sometimes looks like this red line shown in the graph. And that's actually one of the characteristics, or one of the information you can use to see how your models perform depending on perturbation parameter. And then you can identify your optimal perturbation parameter threshold, which you can use, you know, for the analysis. So for example, most of the time you see that people using 80-20 split, which, you know, can be demonstrated by looking to the ROC curve and see where it leads already to reasonable accuracy and precision and recall function. So obviously the diagonal one is basically a random prediction. So in that case, you know, you would see that situation. And if you see that, you know, your receiving operating curve is approaching that line, that, you know, you need something to worry because it's something wrong with either your data or the model, but definitely something needs to be changed. Okay, so what are the properties of receiving operating curve? So obviously, when we look at the area, because that's one of the questions, and sometimes most of the people ask, like, what is the area under the ROC? And, you know, it will tell me how good is your model. So obviously, if the area is one is a perfect prediction, so it's a 0.9 is the excellent prediction, and you can see like a degradation. So obviously, if it is 0.5, it's basically a half of your unit square, right? So it's a random prediction. And if it's below, you know, it's definitely something wrong. But I would say even when 0.5, it's already, you need to start to worry, because it means that, you know, definitely something happening there. So and you need to address this one. So most of the time for the biological observation, so you probably would see receiving operating curve in the ballpark of the between 0.8 and 0.9. So if obviously you see something like extremely good, like 0.99, then you also could start challenging, like what did they do, like why it's so perfect, and maybe there is fetch factor somewhere involved in the developing of the model. But anyway, most of the application is between 0.8 and 0.9, so which seems to be quite reasonable given the our understanding about the biology and some of them measured data. So there are some other key points. We can quickly go through them. Again, I think what you just need to remember that as close as your area is 1 is better. So it means that maybe you just need to get back to that picture and then have a look at the curve. So if your area is getting to 1, you have to have like a very sharply growing curve up and then pretty much go to the flat, right? So that type of shape of receiving operative curve means that you have a very good model. Most of the time you see like something like that, so which will correspond probably for 0.7 area. Not necessarily you would get monotonic curve, so that's else important to remember, because most of the time people accept that, oh, I've seen that in the textbook or in other presentation or lecture that the curve should look like that. Why the curve is very different to compare like what my expectation tells me. This curve is generating for very well constructed model in terms of like not so complex, the data is good, and then you can show that you can get that monotonic behavior. But in real life application, that could be really non-monotonic. It's not something completely red flag. It occurs very oftenly, but still, you need to compute the area under the curve and see what is the value it provides you, because that's one of the characteristics to measure this one. In our situation, that it could be going sharply up and then oscillating around particular value, let's say like around the 0.8 instead of monotonically grow. And that could be a manifestation of the fact that the machine learning model you build is missing additional variable. So basically it kind of does not allow you to fit observable phenomena. It contains some information, but it's not exhausted in terms of the coverage of the phenomena. So it could be a manifestation of something else as well, but that's something you need to keep in mind and then be aware about that. Okay, so in summary, we talked a little bit about basic concept and quantifying the accuracy. So obviously accuracy, we called about precision recall, we called about area under the receiving operating curve. Remember, the receiving operating curve is basically a diagram on the graph of the true positive rate versus false positive rate. So if you compute those informations, you put the points and then you can build that curve. You compute the area under the curve, and then it provides you a necessary assessment of the quality of your machine learning and how good you are. By looking at the dynamic of the curve or the shape, you can also figure out some of the aspect related to your data. It could be that you are doing something wrong because you have like random prediction pretty much, and it could be also the indication that some of the variables are missing to complete the very good description of your phenomena. Keep this in mind, and obviously we can generalize it to the more classes, because we talked about the true positive, false negative, true positive, true negative, true false positive, false negative. So we talked about this in the concept of the 2x2 confusion matrix, but also it can be generalized to more classes, because most of the problems also will be multi-categorical classification. So in that case, we will just basically, usually what people do is just define sensitivity, specificity for each of their class, which is still connected to some other quantities we discussed here. And then they using those, and then they compute the average across all cohorts, sensitivity, specificity, and use this as a metric to measure the quality. And we'll go for that example during the case study.